Hi everyone, I'm Janavi Patel. Today we're looking at double machine learning, a framework for moving past simple correlation to find true causal effects. As a bank manager, you might see that active members stay longer. But is that because of the program or because active members are just wealthier? DML helps us isolate that specific active member effect by stripping away the noise of other variables. Before we run our first model, we have to address the most critical step, causal data preparation. Unlike standard machine learning, where the goal is simply to maximize predictive accuracy, causal inference requires us to be surgical with our data. In the notebook, I've implemented a pipeline that handles missing values, which are especially dangerous in causality if they are linked to the treatment, and performs feature selection based on causal theory rather than just correlation. By using the directed acyclic graphs, or DAGs that you see here, I ensure we are controlling for true confounders like age and geography, while avoiding colliders or mediators that could actually bias our results. This preparation is what allows the DML algorithm to isolate the clean signal we're looking for. In our first example with 10,000 customers, we look at high balance accounts. A naive comparison shows these customers churn 6.7% more than others. But high balance customers are older and have higher credit scores. After running DML, we find the true causal effect is only 2.3%. This means 65.3% of that original correlation was actually just spurious noise from confounding factors. DML revealed that the bank's risk wasn't as high as the raw data suggested. What makes DML so powerful is its versatility. While we just used it for a binary outcome, whether a customer churns or not, the exact same logic applies to continuous variables, like dollar amounts. This transition is key. We are moving from predicting a yes/no probability to predicting a specific numeric impact, using the same cross-fitting and residualization techniques to ensure our estimates aren't biased by the flexibility of our ML models. Now, let's look at a marketing scenario. Naively, it looks like having children causes a $348 drop in annual wine spending. That sounds like a lot. But parents often have different income levels and ages. Once we apply DML to adjust for these, the causal impact drops to just -$95.16. In this case, 73% of the naive estimate was spurious. We also see heterogeneity. The spending drop is 4 times larger for high-income families than for low-income ones. To prove our math works, I built a synthetic test with a known ground truth of 6.02. A naive analysis overshot this at 7.72 due to built-in bias. My DML model, however, recovered a near-perfect estimate of 6.65. This validation confirms that even when the data is complex and the truth is hidden, DML's use of Neyman orthogonality allows us to stay remarkably close to the real causal effect. In summary, DML allows us to use high-performance machine learning while maintaining the gold standard of causal proof. We've shown that over half of the correlations in our business data were misleading. By focusing on the true causal effect, we can make decisions that actually drive ROI. Thank you for walking through this notebook with me.